Hello everyone, I am Sanket Singh and welcome back to my channel. So guys, in this particular video, we are going to continue our discussion on the time and space complexity analysis series. We have already released 3 parts of this series where we talked about from the very foundational basics of time and space complexity analysis. We saw what is experimental and asymptotic analysis, how exactly CPU works, and the best, average, and worst case analysis of algorithms. Now it's a good time to actually do some hands-on and try to see how exactly you can also calculate complexity of a few problems. We are going to take some algorithmic examples and try to take a deeper dive into time and space complexity analysis. This is going to be a pretty power-packed lecture as well. So without any further delay, let's just start. But before starting the video, if you have not yet subscribed to the channel, do consider subscribing it. We are going to put some really awesome educational content all together here. So let's just start. So guys, before moving forward, there is a very important information that I would like to give you. So recently we wrapped our Elite 1.0 front-end development course, and now we have launched our Elite 2.0 advanced front-end development course. This is a bigger and a better front-end development course that you need. This course doesn't need any particular prerequisite, and we are going to take you from the very beginner level to the advanced level of front-end engineering. We have actually included projects like your own Replit clone, Wix website maker clone, right? Uber clone, and a lot of similar projects. We are going to make your own PubSub library based LLD driven projects, and we are going to make sure that you learn important front-end design patterns as well. I'm going to list down all the projects and all the important design patterns here. This is the only course that you need if you're aiming for SD1 or SD2 or SD3 kind of roles, because we are going to take everything to the very advanced level in front-end engineering. We are going to learn a lot of optimizations, and we are going to see technologies like Next.js, Redux, Zustand, TypeScript, React, and of course, the latest version of React. This particular course is going to make sure that you have ample amount of projects that you can add in your resume. We are going to make approximately 20 plus projects with different variety of complexities, engineering problems, and of course, there will be a lot of discussion around the core concepts of frontend. So what are you waiting for? Check out the course link in the description below, and you can use the coupon code mentioned in the description section to get maximum discount possible. See you guys in the cohort, and let's get back to the video. Now we have talked a lot about the worst case analysis, but sometimes in some algorithms, we also need to take a look at the best case analysis, because sometimes what happens is, let's say there are two algorithms, algorithm A1, algorithm A2. The worst case of both the algorithm is same, but then we have to decide still which is the better algorithm. Then we try to decide them based on their average case and the best case, because if the worst case is same, we try to look at the average case, we try to look at the best case, right? So there are algorithms, for example, like bubble sort. You will read about bubble sort when you will move ahead in your programming part, right? And there is one more algorithm like selection sort, right? Now both of these algorithms have got their worst case complexity as order of n square, but still we have to decide which one of them is better. So there are other criterias. One of the criteria is which one is having a better best case. So bubble sort has a better best case. In the best case, it works in omega of n, right? So it's important to understand the best case analysis also, whereas selection sort works in omega of n square only. So we'll talk about this omega notation, and we'll talk about the best case analysis. Best case analysis. We are technically talking about big omega notation, right? What is the best case analysis and what is this omega notation, right? So if I talk in terms of mathematical notation, so we can say that, let me draw a graph, or let me just quickly get a graph for you guys. So what we can say here is that if you take a look at this graph, so we can say the big omega notation gives the tight lower bound of the given algorithm right? So we say that, let's say if we have a function f of n, if we have a function f of n, right? Then we can say that for n greater than n naught, for n greater than n naught, f of n will be greater than or equal to Cg of n, which will be greater than or equal to 0. What does this inequality denotes? This inequality denotes that if f of 1, what is the least value that f of 1 can go to? F of 1 can never go lesser than Cg of n. That is, if f of 1 works in the best possible way, then what's the best case there, right? If it has to work in the best way, what's the best possible case? That f of n will never go lesser than this. This is the least value that f of n can go to. So we have to approximate the least value that f of n can go to. And that particular function g of n, we call it as omega of g of n. We call it as the best case of f of n. We call it as the best case of f of n, that if your function f of n has to work in the best possible way, in some cases only, if your function has to perform the best, this g of n is going to be the best approximation for that. It is never going to go lesser than Cg of n. It will be always at least Cg of n or greater than Cg of n. You can see this here, right? That this inequality denotes that f of n is at least Cg of n or greater than C of g of n. It can never do better than Cg of n. That's the best case analysis. Right? So if I take an example, in front of you, right? Let's say f of n is equals to 5n square, right? And we have to calculate the big omega for this. Then we can say that C is equals to 5, for C is equals to 5, and g of n is equals to n square. We can say it is equal to big omega of n square for all n naught equals to 1. The value of n naught will be equals to 1. That is, this function 5n square is going to perform the best that it can perform is going to be 5n square. Otherwise, it will always perform worse than 5n square. It will never perform lesser than 5n square, right? So if you see it in terms of complexity, in terms of some coding implementation, so let's say if I write a function, let me remove it. Let's say if I write a function f of n, right? And then let's say we say that we have an array, right? And inside this array ARR, I have to search for this element n. So what will I do? I'll just loop over the array. Don't worry. Again, as I said, this is all language agnostic. So what I'm doing is I'm looping till the length of the array. And we say that if ARR at I equals to n, we return I. Otherwise, we return, let's say, -1. So if you carefully see, what I'm trying to do, I'm trying to search for the element n inside the array. Now, what will be the best case? The best case is going to be that the element is present on the 0th index only. Let's say this is the array. And there was 3, 4, -1, 2, 5, 6. And the value of n was equals to 3. So 3 is present at the 0th index only, right? So your for loop will run. And on the 0th index only, you will detect the element and you will return it. Can I say that? In that case, you will just do one iteration and boom, you are done. You don't need to go to the remaining elements. So we can say that the best case of this function, is going to be what? Omega of n. But what will be the worst case? Worst case, you can say that maybe let's say n is equals to 30. That is, it is not even present in the array. If it is not even present in the array, you will read all the elements, all the n elements. You will like let's say there are total x elements. All the x elements you will read, right? Let me give better notation. Let's make it as element. Okay, let's make it as element and let's keep n as the length of the array. So let's remove this. I wrote it by mistake. So what I'm saying is, in the best case, maybe there can be a case that at I is equals to 0, you found the element. So you will do constant operation. Whereas in the worst case, what can happen? The element is not even present in the array. So you will read all the n indexes. right? That means in the worst case, you are going to do order of n. But in the best case, you will do omega of 1. Whenever there is a constant number of operations, no, see, if we found it at the zeroth index only, so you just do constant operation. Whenever we overall do constant operation, now constant operation can be one operation, two operation, let's say 15 operations only. We are never going to go beyond 15 operation. We just represent it by 1. So even in the worst case, if the worst case is constant, so we say O of 1. The best case is constant, so we say omega of 1. So here it will be omega of 1. So omega technically denotes that if the algorithm is going to perform good, how good, like what's the best case for it? What's the tightest lower bound? It can never go beyond this. It can never go lesser than this. That is our case, right? That's what best case analysis works on. But majorly when we are doing algorithmic coding, when we are developing softwares, we generally care more about the worst case, because worst case generally occurs with a much worse complexity, taking much more time, and that's what we have to optimize also. So we are majorly concerned about the worst case analysis. Now we have one more complexity case, that is average case. Now when we say average, then it's not the worst possible case that can occur. It's not the best possible case that can occur. It's like an average that, let's say, you run it for 100 different samples or 100 different type of input. On an average, how does it perform? On an average, like, you're not just considering one case where it was performing extremely good. You're not just considering one case where it is performing extremely bad, but instead you take an overall average of multiple operations. Let's say, let's just take a case. Let's say some algorithm is taking, sometime it just take one iteration for some cases, but for some cases it takes n iteration. For some cases it takes n by 2 iterations, and so on. So what do? You just sum up all the iterations and divide it by total number of operations that you actually did, which will help you to get an average number of operations that happens, or average number of instruction that goes on per operation, right? That's what average case is. In average, we just take a look at overall average picture of the algorithm, that we consider that some of the cases will be very good, some of the cases will be extremely worse, some of the cases will go on average. How does it perform? So there are special algorithms. For example, quicksort. There is an algorithm called as quicksort. Quicksort relies a lot on the average case complexity, because the worst case of quicksort is very bad, but that worst case now occurs with a probability of, like, the probability of the occurrence of the worst case of quicksort is very less. Like, you can say that it will never even occur. Sometimes the probability is so less that the worst case of quicksort doesn't make it a very bad option. We'll learn about, we like later when you will learn more about around algorithmic analysis, we learn about quicksort. But the thing is, the main thing about quicksort's complexity is that the worst case of quicksort occurs very less number of time. The probability of occurring of quicksort's worst case is very less. That's why we choose quicksort, because of the average case, because on an average quicksort performs very good, right? Similar thing exists with addition of new elements in arrays. If you have to add new elements in the array, there is a very efficient way. I'll talk about it. That efficient way sometimes perform very bad, sometimes it perform very good. So we are not able to analyze. That's why we rely a lot on the average case analysis, right? So that's what big theta is. Big theta works on an average, that overall how does the performance of the algorithm looks like. But still we are more concerned about the worst case rather than average or best case, because even if the worst case hits once, it's still very bad. So majority of the analysis that we are going to do is going to be around the big O notation. So now let's start talking about how you can analyze the complexity, time complexity, space complexity for a recursive code. Till now we have done everything with respect to a iterative piece of code. Now we need to talk about recursive code. So overall the theory remains same. The theory remains same, that is, we have to do the time complexity analysis using the number of instructions executed, right? We are going to again use how many number of instructions are total executed with respect to the input, right? The time is going to be measured as a unit with respect to the number of instruction executed to the given input. As the input will grow or as the input will change, the number of instructions will change, and hence that will lead to a change in the time complexity analysis. Okay, cool. Now, technically in recursive codes, there are two techniques. There are two techniques. One technique that we are going to talk about today, right? One more technique is going to be used for some specific type of recursive relations, right? Those are called as divide and conquer relations. Although the baseline theory still remains same, that you have to figure out the number of instructions executed. But we can formulate a few general situations for both of them, right? So the underlying behavior is going to be same, that we have to see the number of instructions that are going to get executed with respect to the input, right? First of all, let's just take our basic recursive codes. So let me take a code like this in front of you, right? So if you just carefully see, then this is a normal factorial function. This function can calculate factorial for you. See, this is the recursive relation for factorial, right? F of n is equals to n into f of n minus 1, right? Okay. Now we have to calculate what is the time complexity for this factorial function. Now the time complexity we have to calculate based on the fact that how many total instructions were executed in order to calculate n factorial. How many total instructions were executed to calculate executed to calculate n factorial, right? Now just think about it. Here we don't have a loop. We don't have a loop, right? Instead, we are using recursion to repeat the process. So how many total instructions will be there? Just think about it. Let's say if you call for f0 of 5, right? If you call for f0 of 5, what will happen? F0 of 5 will first go to this if check. Is 5 equals to 1? No. So we executed one instruction. Can I say that? This if check is what? This if check is not a loop, right? It's independent to the value of n. It is independent to the value of n. So we can say it's going to take constant unit of time, right? And then it goes to the next line. It goes to the next line. It says return n into and a function call. See, the product of two values is constant. Product is a constant operation, and calling a function is also a constant operation, right? Just calling a function is also a constant operation. There is no loop acquired at all, right? So can I say when you call for f0 of 5, you do this as a constant operation and two more constant operation, that is constant plus constant is still constant. So I can say when you call for f0 of 5, overall you executed constant number of instructions. But here is a catch. By just executing f0 of 5, your whole program is not done. Why? Because when you make this function call, there are two things that are happening. Here. One is we are calling the function. This is the first step that is happening. And calling the function is a constant operation. When you call the function or when you invoke the function, that is a constant time operation. But when you call this function, and this function goes in the call stack, because we know that whenever there is a function call, even if it's a recursive function call, you add it in the recursive call stack. So initially called for f of 5. Now you're going to call for f of 4. Now whatever time this f of 4 is going to take is going to be extra apart from the function call. Can I say that? By just writing f of 0 n minus 1, this is just we are calling or invoking the function. Once we invoked the function, this function came in the call stack and we are here waiting. right? Now, how much time this function call is going to take to execute is going to be the extra time. So we have to add that. That is how much time f of 4 is going to take. That is going to be the total time. Yes or no? Okay. Now let's see how much time f of 4 is going to take. If you go for f of 4, you will again compare. Is 4 equals to 1? No. So again a constant time operation. Then you say return n into. So there is a product which is a constant time operation. F of n minus 1. So when you say f of n minus 1, that means you're calling for f of 3. So we are calling the function first. So again, total constant time operation you are doing. See, this if check is constant, product is constant, and calling the function is constant. Once you called the function, it called for f of 3. Now, how much time f of 3 is going to take to completely execute itself is going to be the extra time. So the total time executed or total instructions required to calculate n factorial or 5 factorial is this plus whatever time f of 3 is going to take, right? F of 3 is also going to take constant operation of time, and internally it is going to call for f of 2 and so on, right? And so on, f of 2 will call for f of 1 and so on and so forth. So what I'm trying to denote here, I'm trying to say that in these kind of recurrences, the total number of instructions can be calculated very easily by saying that number of instructions in one function call multiplied by total number of function calls. Now this is not a general formula. Because there will be cases when this formula might not work. For example, as I told you that there are some special type of recursive relations called as divide and conquer. We'll talk about that. We'll talk about divide and conquer relations, but a lot of recursive formulas we will be able to detect once we will be completing the learning of divide and conquer relations. Then we will be able to very easily detect which recursive relation is a divide and conquer relation and which is not, right? So all those relations which are not in divide and conquer relation can be almost 99% can be very easily generalized with this formula. Because just think about it. However many number of times you are going to call f of 0, right? Most of the time, until or unless the code that is written in the function is dependent or putting a loop based on this input, till that time every function call is going to have the same number of instructions. Just think about it, right? So this is going to be the number of instructions. Just think about it. Every time the number of instructions are same. The number of instruction would have been different if, let's say, I would have introduced a for loop that starts from 0 and goes till n. If I would have introduced a for loop like this, then because in every function call the value of n is changing, then this formula will not work, right? But if the situation is something where the recursive relation is not changing the total number of instruction in every function call, then we can use this formula. That is number of instructions in one function call multiplied by total number of function calls. Because here you can see in f of 5 also there is same number of function calls, f of 4 also same number of function calls, f of 3 also same number of function calls. That means that number of instructions of every function call is same. So total number of instructions will be number of instruction in one function call multiplied by total number of function calls. Now just think about it. If this is the function, in every function call you are doing constant operations, and how many total function calls will be there? From 5, this is the first function call, this is the second, third, so on and so forth. Can I say you will make n function calls? From 5 to 1, you will make n function calls, right? In every function call, if you go to this function, in every function call you are making constant operation, there are total n function calls. So can I say total instructions are nc? And what is the complexity for this? The time complexity is going to be order of n. The time complexity is going to be order of n, as simple as that, right? So this is something that we have to do. And as I say, we have to keep a check if there is a divide and conquer relation, or there is a situation when the functions of recursion are executing different number of instructions in every function call, then we have to manually calculate it. And it was similar in loops also, right? When the constraints of the loops are same, like n, and internal loop is also n, then we were able to very easily decipher n square. But when the overall parameters of the loop change, then we have to manually calculate it, right? Similar thing will happen here. If we can just straightforward see that, okay, in every function call, you can see there is a base case, and then there are few products. Calling a function is a constant operation, then it's like overall constant operation. Now, internally, that function is going to be called multiple times. And due to that, we are going to add up a time complexity. And that's why we can use this formula. So we're going to solve a few more questions to get a better hang of it. But this is the overall agenda that we are going to do for basic problems of recursion. Later, we will try to understand what is special with divide and conquer. So now we have a new problem in front of us. You can see this is also a recursive code, and if you just carefully analyze, it's a Fibonacci code, right? Okay. Now in Fibonacci, you can see that with respect to n, the total number of operations in every function call is same, right? You can see if you go for f of 5, f of 5 calls for f of 4 and f of 3. F of 4 calls for f of 3, f of 2. F of 3 calls for f of 2, f of 1, and so on, right? So there are multiple function calls that are happening. In one function call, you can see you are having a if check, which is a constant operation. You're having one function call which is constant, you have another function call which is constant, and you are doing addition of the answers of these function call which is constant. So in one function call, overall, you are doing constant number of operations. In one function call, we have constant operations. And how many total function calls we can have? Just think about it, right? Just think about it. If let's say you have to calculate f of n calls for f of n minus 1, f of n minus 2. F of n minus 1 calls for f of n minus 2, f of n minus 3. F of n minus 2 will call for f of n minus 3, f of n minus 4, and so on, right? And so on. You can see that from n you go to n minus 1 and n minus 2. If you just see the longest path, for example here, if you see the longest path, then f of 3 calls for f of 2, f of 2 calls for f of 1. If you see the longest path, then in the longest path we are making what? N calls. But it's just not n calls here. Technically, we are expanding like a tree. We are expanding like a tree, right? We are expanding like a tree. This is f of 1, f of 0. This is f of 0, f of 1, f of 0, right? We are expanding like a tree, right? You can see that when you are very close to the lower values, then some of the values are empty. You can see, if you just see this much part, then this tree is completely like full. But here you can see some of the children are not present. Some children are not present, right? So when you reach the very small values, then you can see some of the values are gone. But if you see with respect to very high value of n, let's say n becomes as big as 10 raised to the power 2 or 10 raised to the power 3, then a very big part of the tree is going to be something like this: f of n minus 1, n minus 3, n minus 3, n minus 4. Then here we'll be having f of n minus 3, f of n minus 4, and so on. And if you just carefully see, then every level has some function calls. If you see this level, there are 2 raised per 0 function calls. If you see this level, there are 2 raised per 1 function calls. There are 2 raised per 2 function calls, and so on. So we are having function calls with respect to power of 2. So what is the total number of function calls? Total number of function calls is going to be what? Approximately. I'm saying approximately. I know that at the very last level, there will be some calls which are going to be missing. But approximately, if we assume that everything is present, right? If we assume everything is present, then we'll be having something like 2 raised per 0 plus 2 raised per 1 plus 2 raised per 2 plus 2 raised per 3, so on and so forth. right? This is what coming as a geometric progression. Can I say that? And thus, if you see the sum of this geometric progression, sum of this geometric progression is going to be what? First term is 1 into ratio is 2 raised to the power. Total number of terms. Now just think about it. This is 2 raised per 0, 2 raised per 1, 2 raised per 2, 2 raised per 3, 2 raised per 4. So n was 5. So you're going to 2 raised per 4. So final term is going to be 2 raised per n minus 1. That is approximately, this level is going to have 2 raised to the power 0 function calls. This level has 2 raised per 1 function calls and so on. Final level will be having 2 raised per n minus 1 function calls. So from 0 to n minus 1, total level becomes n minus 1 upon 2 minus 1, which becomes what? 2 raised to the power n minus 1. Sum of this GP is what? 2 raised to the power n minus 1, which is approximately 2 raised to the power n. So we can say overall, in approximate terms, there are 2 raised to the power n function calls. There are 2 raised to the power n function calls. So in one function call, you are doing constant operations. Total number of function calls are 2 raised per n. So time complexity becomes what? 2 raised to the power n into c, which is order of 2 raised to the power n. Can I say that? So the time complexity of this function is going to be order of 2 raised per n. And you might get a feeling that, okay, sir, but at the last level, you are not having 2 raised to the power 4 function calls. Instead, you are just having 2 function calls. That's what asymptotic analysis is all about. We approximate things. Because if n will become extremely high, 10 is per 4, 10 is per 3, 10 is per 5, then even if you have pruned some calls at the very last, it will not matter, because let's say you prune all the calls from the last level and you go from 2 raised per 0 to 2 raised per n minus 2, let's say. Still the overall sum is going to be 2 raised per n minus 1, and 2 raised per n minus 1 is approximately 2 raised per n. So in approximate terms, things are not going to change, and hence the complexity of this Fibonacci recursive code is order of 2 raised to the power n. And if you just carefully analyze what is the complexity of iterative Fibonacci, I'm just writing a pseudocode here. In pseudocode, if you remember, you start with 2, you go to n, you do plus plus, and you do c is equals to a plus b, right? Then you say a is equals to b, b is equals to c. Remember? Right? And at last, in the value of c, you have the nth Fibonacci. So you can see from 2 to n you are going. So from 2 to n, there are what? Total n minus 2 function calls, which is approximately n. In every loop, you are doing one addition, 2 assignments, 1 comparison, 1 increment. So 5 instructions. 5 into n is approximately n only. So the complexity of this iterative Fibonacci is order of n, whereas the complexity of recursive Fibonacci is order of 2 raised to the power n. And if you remember, the growth rate of 2 raised to the power n is much higher than order of n. That means this piece of code is slower if you compare it with the iterative code. This iterative code, if you see, that piece of code is slower. Although there are some techniques using which you can optimize this code. There are some techniques using which you can optimize this code, but those techniques are currently out of the scope for this particular lecture of time complexity. So there are techniques like dynamic programming and all, using which you can optimize the overall time analysis, right? But my point being, if you just go with the plain recursive Fibonacci code, then the complexity is order of 2 raised to the power n. And if you go with this plain iterative Fibonacci code, this is order of n. Hence, this iterative code is better. But again, there are few techniques using which you can optimize both. One small piece of note. This approach of order of n is also not the most optimized approach. There exists an approach using which in order of log n, you can calculate nth Fibonacci. That approach is called as matrix exponentiation. You can read about it. That approach is called as matrix exponentiation. So using some matrix multiplication and matrix analysis, we can calculate the nth Fibonacci in order of log n time. So just a trivia I want to share with you. So now we have a new function in front of us. Now this time, if you just carefully see, inside the function, which is technically a recursive function, because we are calling the function again, we also have got a for loop. So it's now no more like constant number of operations, first of all. Second of all, this for loop is dependent on the value of n. So now we cannot just directly use that formula, right? Now we cannot just directly use that formula. So we have to carefully analyze the question and then only figure out what can be done. Now, generally, in order to analyze the questions like these, I try to take some simple examples. Just think about it. What if I call for f2 of 5? If I call for f2 of 5, this if check is a constant operation plus. This loop is going to go from 1 to 5. Can I say there will be 5 iterations? And then there is a function call. And then there is a function call. So again, a constant operation. And this loop is also going to execute constant number of times. There are some constant operations here. So for f of 5, you technically did something around 5 plus 2c operations. And then you called for f2 of 4. In f2 of 4, you are going to do constant number of operations plus you are going to run a loop for 1 to 4, which is 4 iterations. And then again, make a function call f2 of n minus 1. That means you call for f2 of 3. In f2 of 3 again, we can write something like this. There, the loop is going to go for 3 iterations and so on. Finally, you will be having f of 1. The loop will just go for 1 iteration and that's it. So technically, if you see, you are doing 5 plus 2c plus 4 plus 2c plus 3 plus 2c and so on. Something like this. So if you see it with respect to n, if we consider 5 as n, that means you are doing n iterations plus 2c plus n minus 1 plus 2c plus n minus 2 plus 2c and so on up till 1 plus 2c, right? This 2c is what? Constant operations. So constant operations so we will avoid. We are left with what? N plus n minus 1 plus n minus 2, so on and so forth, plus 2 plus 1. This is what? Sum of the first n natural numbers. What is the sum of first n natural numbers? N into n plus 1 by 2, which is what? N square by 2 plus n by 2. In big O notation, this term is going to get avoided because this is a lower degree term. And 1 by 2 will also be avoided because it's a constant. So in big O notation, this will be order of n square. So the time complexity for this function is order of n square. So here we manually analyze that, okay, in one function call, you are executing n iteration. Then you are calling for n minus 1. So in the next function call, you are going to execute n minus 1 iterations for the loop. Then you will call for n minus 1, that is n minus 2. So in this function call, you will execute n minus 2 iterations for the loop and so on. So we will just sum up all the number of total iteration, which will give us this as the total number of iteration approximately. We will just resolve it, avoid the lower degree term, avoid the constant, and order of n square is going to be our final time complexity. So this is going to be the answer for this question. So I hope the overall logic on how we are checking recursive time complexity is clear to everyone. Now this is a new recursive code in front of us and we have to calculate the time complexity for this code. Here in this code, we have to assume that this ARR is actually an array and the length of the array can be considered as k. Okay. Now just think about it. If you just carefully see this function, you are doing recursion with the variable n. The value of the variable n changes every time, right? From n to n minus 1, then to n minus 2, then to n minus 3 and so on. The array length remains as it is. The array length is constant every time. That is k, right? So in every function call of f3, you execute a loop of order of k. This loop is of order of k. In every function call, you execute this loop. This is a constant operation. Calling a function is a constant operation. So can I say every function has same number of operations, that is order of k, right? And what is the total function calls? What is total function calls? Total function calls is from n you go to n minus 1, then you go to n minus 2, so on and so forth. You go to 0. So on an average, approximately there are n function calls, right? There are n function calls. So total function calls are n. So can I say total operations will be order of n into k, and this will be our time complexity as well. As simple as that. So now here you can see in this question, the number of operations that was executed in every function call was same. So we were able to just directly apply the formula, right? So we have to just keep our mind open. We have to just see the situation, what is the expected situation, what is being done. And based on that, we have to calculate our answer. So I hope the overall logic of the problem is clear to everyone. So we have now a new problem in front of us, function f of 4. This function looks a lot similar to the Fibonacci function, but the only difference is here we call for n minus 1 two times. Here we call for n minus 1 two times instead of calling for f of n minus 1 and f of n minus 2. So if you see, from n you call to n minus 1 and n minus 1 only. Then from n minus 1 you call for n minus 2, n minus 2. Same here, n minus 2, n minus 2. Then from n minus 2 you call for n minus 3, n minus 3, n minus 3, n minus 3. Right, and so on. So you can see at each level we are having number of function as a power of 2, so on and so forth. At last we are going to have 2 raised per n minus 1, and in one function call you are having constant number of operations. So the overall time complexity is going to be 2 raised per n, total number of function calls multiplied by time in one function call, right? But I will change the function very slightly. If let's say if I have a function f5 of n, and then I say n less than or equal to 1, then let's say return 1, otherwise return 2 into f5 of n minus 1. Now technically what I have done here is, in the previous function call it was f4 n minus 1 plus f4 n minus 1, which is technically what, 2 into f4 n minus 1, right? Like we could have written 2 into f4 n minus 1, but we didn't. We manually made two function calls. But here, instead of making two function calls, what I'm doing, I'm making function call once and multiplying it with 2. So let's see what's happening. Now if you just carefully analyze this, from f of 5 of let's say 10, you make a call to f of 5 of 9. You are now not making two function calls. You're only making one function call. Then from 9 you're going to call for 8, then for 7, so on and so forth, 3, 2 and 1, and then 0. The moment you get 0, you're going to return 1. Then whatever is the answer here, you're going to multiply 2 with it and then return it to this. Then whatever is the answer here, you're going to multiply 2 with it and then return here. So you can see we are only making n function calls, and in every function call we are just doing a constant operation and a multiplication. So the time complexity for this case is going to be order of n. So in recursive code, the way you call the function can determine a lot of things. The answer of both of the codes are going to be same. The final answer from both of the codes are going to be absolutely same. It is just that here we are only making one function call and using the result to multiply it with 2. But instead here we were manually making two function calls, which was like manually going and calculating all of these operations again and again, and then adding both of them. So the way you actually implement your recursive functions can determine a lot of things. So I hope the overall answer of the problem is clear to everyone. Now let's start talking about space complexity. Now see, space complexity is also one of the most important metric that you have to measure when you are writing algorithms, because how much space in the RAM your algorithm is taking can determine how your application overall performs on the device, right? Now devices can be of very huge amount of memory of RAM and very less RAM memory also. So you need to make sure that your overall algorithm is efficient in terms of space also, right? Now this space complexity also we measure with respect to asymptotic analysis only. If we measure it using asymptotic analysis only, that means we are going to measure space also with very high value of n. If there is an algorithm which is taking more space for very less value of n, but it is overall efficient with very high value of n, then we are going to prefer that particular algorithm. Same theory is going to go here. Now, space also you are going to see space taken with respect to change in input. Like if your input is changing and the space that you are taking is changing, then only it is going to account for a space complexity. if the input is changing and the overall space that you take is always constant, doesn't matter if the input is of 10 to the power 5, 10 to the power 6, 10 to the power 7, the amount of space that you take is same always. Let's say 100. Always you take the same amount of space, then the space complexity is going to be constant because the rate of growth of space is going to be constant. So for example, if let's say if I write a function f, and inside this function I make a few variables, let's say a is equals to 10, b is equals to 20, c is equals to 30. Now if you just make a few variables, let's say you made 20 variables. Now just think about it. If the value of n is 10, then also you are going to make 20 variables. If the value of n is 10 raised to the power 5, then also you are going to make 20 variables, right? So by just creating a few variables that are not changing with respect to n is not going to add any space complexity. Whereas if you use any data structure, for example, arrays, or maybe kind of like a map or something you use, right? Then let's say you create an array of size n always. That means now you're using some constant space, and along with that you're using some n extra space of the array. So the overall space complexity will become order of n, right? Now one very important thing to note in space complexity is 99% of the time, until or unless specifically asked, we do not consider space of input array or any other data structure. Like in a lot of questions, you might have seen that you get array as the input to the function. Right? So if something is given to you as the input, that means your algorithm has not created that space manually. It was part of the input. So you do not consider that input array, or similar to input output also, your input output array you do not consider. But let's say if you are using some auxiliary extra space in order to do the computation, right? If you're taking some extra space using which you are preparing your answer, right? Then that extra data structure or array you are going to take, not the one that is given to you in the input or for the output, right? For example, you might have solved the question where you are given two sorted arrays and we have to merge them to create a new sorted array. Now in this algorithm, we generally take an extra array. We take an extra array C, and this extra array is of size n plus m. And in this extra array, we fill up all of our elements. We create the answer. And then from this array C, we port the answer to the given array A, right? This is a question given on LeetCode also. This problem you can find on LeetCode also, right? In the problem on LeetCode, you'll get an input array A, input array B. Both of the arrays are sorted. Size of the array A is n plus m. Size of the array B is m. But A is only filled with n elements. Remaining m elements are all zeros, right? So in this kind of a question, what do? You create a new array C. In this new array, you form all of your answer and then copy the elements of C back inside A, right? So this C is an extra auxiliary space that you are taking. So this is going to account for the space complexity as order of n plus m. But because A and B were already given to you in the input, you are not going to consider that in your space complexity. But sometimes in 1% of the cases, maybe in some interviews or something, some people might say that you have to also consider that in your space. Then you can mention input array also, but 99% of the time, you do not need to mention any space of the input. So guys, if you see, this is the link of the problem on LeetCode, merge sorted arrays. In this function, if you see this solution we can like just directly submit. In this solution, I'm creating a new array of size m plus n, which is the sum of the size of nums1 and nums2. But overall nums1 is also given as the size m plus n only. But the remaining n elements are filled with zeros. So you first merge those two sorted arrays inside a resultant array. And then at last you copy the elements of the resultant array inside nums1. So technically your input is not going to be considered in your space complexity. and the output is given by the same input array only. So this resultant array is an extra auxiliary array that we have created, and hence the space complexity is going to be order of m plus n. Now let's try to understand what should be the space complexity of recursive codes. So if I paste a recursive code in front of you, let's take this, or let's take this. Okay, so this is a recursive code. Now just think about it. Here we are not making any arrays. We are not even like having a lot of variables. There is only a local variable n, right? So how exactly space complexity is going to work here? Now the problem with recursive codes are that there is an extra space always involved with the recursive code. There is an extra space always involved with recursive codes. And what is that extra space? That extra space is the space of call stack, because call stack also exists in the memory, right? Call stack also exists in the memory. So you are not taking any array or not taking any other data structure, but you are filling your call stack. If you are filling your call stack, that means you are taking space in the memory. And just think about it. This is a factorial recursive code, right? How many stack frames do you add in the call stack in the worst possible case? If the value is n, just think about it. This is the call stack. You call for f of n, then you call for f of n minus 1, you call for f of n minus 2, so on and so forth. You call up till f of 1. Can I say that? Till the time you compute f of 1, all of the remaining stack frames are in a waiting state. That means at some point of time, the total space that you took is what? Equal to n stack frames. Total space that you took is equals to n stack frames. And in every stack frame, are you creating any other data structure? No. You're just creating a variable n. You're not creating any other array. Let's say if you would have been creating an array for every stack frame, then it would have taken even more space. But you just have n stack frames. In every stack frame, you have a variable. So can I say the space complexity is going to be order of n? That's it. That's it, right? So space complexity of recursive code will involve the data structures dependent on the value of input that you make inside the function plus the call stack that you have made. So even if you don't create any data structure in your function, recursive codes are always going to take space in the memory because the call stack definitely takes some extra space, right? Now, what if we have something like this? Let's say we have something like this. Now, if you carefully see, this is what? Fibonacci. This is Fibonacci, right? In Fibonacci, let's just think about it. If you remember, I told you, right? The recursive code doesn't work parallelly. Let's say if I call for f of 4, f of 4 calls for f of 3, right? F of 4 calls for f of 3, f of 3 calls for f of 2, f of 2 calls for f of 1. F of 1 is a base case, right? So you filled 4 stack frames, right? Okay. Now you're going to come back. When you're going to come back, this will be removed. And now from f of 2, you're going to call for f of 0. F of 0. So can I say till now, the maximum space that you have taken is still 4 units. And when one stack frame removes it, you can just remove it from the memory, right? It doesn't stay in the memory, it gets removed. Okay. So now you go back to f of 3. So f of 2 also gets removed, you go back to f of 3. Now from f of 3, you call to f of 1, right? Now from f of 1, you go back to f of 3. Then from f of 3, you go back to f of 4. So you remove both of them. Now from f of 4, you call for f of 2. From f of 2, you call for f of 1. F of 1 is a base case. You remove f of 1. Then from f of 2, you call for f of 0. F of 0 is also a base case. You remove it. Now f of 2 is also done. You remove it and you are back at f of 4. So if you carefully see, space complexity in a recursive code is not like time complexity, because all of these functions are not always available in the memory. First, all these 4 functions are available. then these 4 functions are available. This is done. Then these 3 functions are available. Then these 2, then these 3 again, then these 2, then these 2, then these 3, then these 3, and so on. So at any point of time, maximum, we have n stack frames. And in every stack frame, you are just creating a few local variables. You are not creating any array or something dependent on the value of n. So the space complexity is going to be order of n, right? So space is different than time. You don't have to see number of function calls or the tree is expanding a lot, whereas here the tree is a bit linear for factorial. So space complexity is going to vary based on that. No, space complexity is going to vary that how much space you take. See, I took 4 stack frames here, but then I removed one. So I'm consuming the remaining 3. One is free. That free slot I gave for f of 4. Then I freed this one also. Now I'm only consuming 3. Then I freed up 2 also. Now I'm only consuming 2. So if I'm at some point of time, you are removing the space, right? You're losing the space. If you're losing the space, that means you're freeing up the space. That means you're not taking more than 4. Maximum at any instance, you take 4 instance. That's it. So that's how you have to compute space complexity. You have to be very smart when you have to look at these questions. You cannot just generalize everything. You have to put in your brain. You have to see how much space we are taking at any point of time, and then only evaluate what is going on and what is not going on. So now we have a new question in front of us. This is f of n. And it again looks like a lot similar to the Fibonacci recursion. It's just that we have one more recursive call. That means at any point of time, we are going to call for f of n minus 1, f of n minus 2, f of n minus 3. Then here also n minus 2, n minus 3, n minus 4, n minus 3, n minus 4, n minus 5, n minus 4, n minus 5, n minus 6. So you can see at every level you have functions with respect to power of 3. So total number of functions are going to be approximately 3 raised to the power n. In every function call, you have constant time operation. So the time complexity is going to be order of 3 raised to the power n. This is going to be the time complexity. And you know that these functions don't grow parallelly, right? That means you are going to see one branch first. For example, if you see f of 5 will first see f of 4, f of 4 will first see f of 3, f of 3 will first see f of 2, f of 2 will first see f of 1. Then f of 2 will call for f of 0. Then it will call for f of minus 1, right? Then f of 3 will call for f of 1, which will call for this, and so on, right? So at any point of time, you are going to take maximum 5 stack frames. Otherwise, these are going to be removed and then you are going to grow here. So the space complexity is going to be same as the space complexity of Fibonacci. That is order of n. This will be the space complexity. So we have to keep on analyzing different type of functions, right? Whenever you solve a question in data structures and algorithm, try to see what is the space complexity, what is the time complexity. This is the only way to practice these kind of things and to make sure that you are getting the best grip possible on questions of time and space complexity.